Okay, so actually, hold on. I'm checking the average, and I don't want to share someone's grade by accident. All right, so lab 1. So the average for lab 1 was an 84%. I think I already mentioned that in like an announcement, but or maybe that was just on Discord. But the average for lab 1 was an 84%, so that was pretty good. Now, yeah, so I think I only mentioned in Discord, but I do grade lab 1 generally a bit more easy than the other labs. So, okay, there's a question. The names of the add-ons, they're Signal Processing Toolbox and then DSP Toolbox. Let me go back to them. Okay, so we have Signal Processing. You can just type that. Oh, that's the first one. So right here, oh, and they actually show the other one right below it. So DSP System Toolbox. So get both of these. Okay, so yeah, lab 1, the average was 84, so that was pretty good. But in general, I grade the first lab easier than the following labs that we're going to have, just because it's the first lab and you don't know what my grading style is yet, or some of you don't know my grading style yet. So be sure to take a look at the feedback. That's kind of a pet peeve of mine when I can tell that some people aren't looking at the feedback, because that's only going to hurt you in the end when you can just easily look at the feedback that I have. And that's going to be pretty quick to look at. Tyler, do you mind muting your mic if you're not going to talk? Because it was there's some echo.
Yeah, my bad. Sorry.
That's good. Okay, so so look at the feedback, and again, I think I only mentioned in Discord, but I'll show you kind of how to go about that. I'm gonna stop sharing my screen again really quick, just because I don't want to show someone's grade by accident. Okay. Okay. So if you didn't already see grading, I'm sure most of you have, but if you didn't, you can basically go into Canvas, click on assignments on the left-hand side here, and click on experiment 1, submarine towing. And then, so right away you see basically my rubric that I have for the breakdown for everything. So you can look at that. In general, I kind of went by these points. I gave you more points than, like I gave you the benefit of the doubt basically. So I tried to give as many points as I could. So you can look at the deliverables again if you, I don't know, forgot what they were. But really I talked about all the deliverables in here. And again, I give you the breakdown. So figure's not fully saved. I guess I show that as -1 point here, but remember from last time I didn't mark you down for that. So if you're missing any points for formatting, it was because of maybe a combination of that and some other things. Okay, so you can see your grade. I think it should show basically your grade here, and you can see some comments that I have for each kind of section of the rubric here. So I kind of did a combination of that and also specifying on your actual PDF, I wrote some comments like annotated on there. So be sure you also look at your PDF. So if you click on submission details, well, of course I didn't upload a PDF here, but you would click on there and then it should open up your, or you might see a different file here, I forget, but you should see your PDF somewhere up here. And if you click on that, then you can see all my feedback, and you can even download a PDF with that feedback kind of annotated on there. Okay, and let's see. So just off the top of my head, there was one big trend that I saw for people. I'm actually going to put in the chat really quick in case anyone else came late what toolbox is to get. I should have done that before. Okay, so there's one big trend that I saw, which was writing the objectives in the abstract. So a lot of you, and of course it's kind of intuitive to think about it this way, but if we go to our lab and we go to the handout, so a lot of you just put the objectives that we have up here, which again, that makes sense, right? You see objectives and you put that down, but um, these are really learning objectives and not so much the objectives of the lab itself. So you want to be sure to basically pretend that you're actually working for some company or something like that, and it was your job to basically to conduct this experiment for them. And in this case, for lab one, to determine or compare two different cable lengths for a submarine problem, and run some tests on those, and basically decide which cable length is going to be the best in quotes, basically the most safe and most cost effective. Obviously, we didn't talk about cost, but that could be some part of your discussion. I think Sean brought that up. That was a good point. So you do something like that and compare the cables and mention the main results in your abstract. And yeah, and then you do quite well for that, I guess, kind of mark on the experiment or the report. So again, just make sure that when you are writing the objectives of the lab, I don't know if it's for all the handouts, but probably for all the handouts, this kind of part here is more of learning objectives. So think about what we're trying to accomplish as a whole for the experiment, and then write that down for the objective. Okay, and then one more thing for the labs. I saw that I don't know, maybe 5 or so kind of reports. The formatting was all weird, and that's not obviously your fault. No one's trying to make the formatting bad, but let's see. I can maybe kind of show you what that would look like. I'm not going to show anyone's memo again, of course not. Let me stop sharing really quick. So basically, I'm just going to go to a file that I have. Let me find one though. Okay. Okay, so this is for my other class, but you see the formatting is all messed up here. This is basically a MATLAB script, so it looks all weird, but um, some of your files kind of look like this for the PDF, and once you upload your submission, you could probably see this as well. So if it looks like this, it's a lot harder for me to grade because I have to open up the file separately, and I like to actually write comments on your PDF so I can have a comment directly by whatever I'm making, a comment on, and I don't need to just rely on writing comments in the rubric. So when you submit it, just make sure that the formatting is okay. Now, I haven't used Word in a while, but I think it's an issue with how you're converting your Microsoft Word document to a PDF. So I'll try to look into that. Um, but yeah, I already saw a few of you that already submitted, which is good. There's some formatting issues still, so I think you might need to try converting it to a PDF in a different kind of method, and then it might look good. So yeah, just look into that, okay? Because I want to make comments directly on the PDF, and it's just a little more cumbersome for me when I have to open up the PDF in a separate location, and then I can't write comments directly on it. Okay, so lab 2, I know we're kind of talking a lot here in the beginning, but lab 2, that's due today, right? Unless I'm insane, but I think that's due today. I think I have it on the calendar. Let's check that really quick. Yeah, it's due today. Okay, so make sure you get that in by 11:59 p.m. And yeah, so I have a deliverables document for that too, so be sure that you check that out as well. If you already haven't, hopefully you have since it's due today. Click on that.
Yeah, I actually had a quick question on that.
Okay.
Um, when you were trying to teach us how to like input the scalable vector images, I don't know if it's like a formatting issue on my end or something, but when I did that, it would make the text come out like windings kind of thing, like just boxes and squares and stuff. So
Oh
I,
yeah, yeah. Yeah, I saw that comment that you had.
yeah, so I just did it as like a JPEG or PNG or whatever because that worked. That's okay, right?
Yeah, it's okay. You should just make sure that you use a DPI of like 300 and then it would look good.
Okay.
Yeah. So yeah, I'll try to look into that too because I know Word can handle SVGs, but yeah, there might be some kind of like a specific way that you have to import it in the document. All right, so I think we're good to go now for the experiment for today, unless there's any other questions on either lab 1 or lab 2.
I did have a question for lab 2. Are we supposed to have sample calcs for
Yeah,
lab 2?
yeah, so that's actually a good question. I'll try to be more specific to you for this lab. I'll make another deliverables handout for this lab today. And on that handout, I'll actually have another section for the sample calcs that I expect you to have. But if we're looking at it here, basically every result that we have, you should have a sample calc for. So theoretical natural frequency, you should have one sample calc for that. Of course, for all of these, you only need to do one per kind of result. So one for the theoretical natural frequency. Have one for converting, this experimental natural frequency we just read directly, right? But we had to convert it to radians per second. So show that conversion here. You only need one for lab view, one for the strobe gun, one sample calc for the effective stiffness, one for the effective mass. So for this, we were looking at our plot here for the least squares plot. So you'd be using the relevant numbers for that.
Okay.
And then percent error two, you just have to do just one. I know we have that for a few things, but do it just once because, I only need to see that, really simple equation. And then theoretical stuff as well.
Okay, thank you.
So yeah, I'll try to be, once I make today's handout for the deliverables, hopefully I can get to that today. I'm going to add the sample calcs that I want to see as well. All right, so today we're going to do the experiment 3. Hopefully it's not too long. So we're going to do that. And if you missed the beginning of class, make sure that you get these toolboxes if you don't have them at some point. If you don't get it today, like right now, that's fine. You can just look at the video afterwards. All right, so let's open up our slides here, and we'll go over kind of what we're going to do today. So I updated basically these slides on Canvas, so I just kind of added some more. Let's see. We got a decent amount here, so these slides are half for me, honestly, and half for you. They kind of help me out to keep everything organized. Okay, so this is where we left off last time, which is basically talking about what we're going to do today. So let's go through these slides just really quick here. Okay, so we're going to have basically an open loop system that we're going to make first, and then we're going to have a closed loop system. So we're going to have two scenarios for our open loop system. We're first going to start out with some kind of roll input. Again, keep in mind that we're modeling basically the response of an aircraft for some input angle or some input roll angle that we have for this system. So if I tell the aircraft that I want to roll by 5 degrees, we should see what the response is going to be. So you'll see for an open loop system, it's going to be god awful, absolutely terrible. You're basically going to die. And then for a closed loop system, we're going to tune our controller so we get a better and better response to what we actually had for our input on the system. Okay, so we're going to start out again with an open loop system. We're going to have some roll angle. We'll look at the output. Then we're going to have some new roll angle that we're going to have And this time we're going to have a bird strike on the plane, and we'll see how that affects our output. And then we're going to go on to the closed loop system. So we're going to start out with the Ziegler-Nichols rules, if I say his name right or her name right. So for that, we're basically starting out with just a proportional controller, so KP, and we're going to start out at 0, and we're going to increase our value for KP until we have a marginally stable system. So that's going to look like this, where we have these basically consistent oscillations in our system. So peak to peak, we have the same kind of value. All right, and then once we get there, that's going to be known as K star. So that's going to be, we say KP is now equal to K star once we reach that marginally stable point in our system. And then from there, we're going to implement the next step for our Ziegler-Nichols rules. And that'll be first, we're actually going to set KP equal to 0.5. Now, I don't show that here, but that's just for one other step in our report that we have to do. And then after that, we're first going to look at that response. And then after that, we're going to kind of implement our last step for tuning our controller. So we're going to set KP equal to 0.45 times K star. Again, K star, that's when our KP value gave us a marginally stable system. And then we're going to add in a derivative controller here, that's KD. So KD will be equal to 0.125 KP, which was, this value right here, times, this should actually say T star. So kind of a little mistake in the report. And T star is going to correspond to our period for our marginally stable system. So T star here would be, here we have peak, we're looking at our peaks here for the amplitude, and we just measure that period. For the lab, it's going to be around 21.8 seconds. All right, and then we're going to look at that response, and we'll also have another bird strike, and we're going to see how our system can react to that. All right, so that's the kind of layout for the lab today. Okay, so let's get started now. So hopefully you have your toolboxes installed. Again, if you don't, that's fine. All right, so the first thing we're going to do, oh yeah, by the way, Adrian, I looked at my laptop, and the screws for the laptop, they're not just hex screws, I think they are proprietary, so I can't open up the laptop. I'm just saying that because my laptop is super loud again right now.
Yeah, you're totally right. I looked it up last class. They use proprietary screws.
Yeah, of course. Yeah, so I'm just gonna open up my script on my laptop. Okay. All right, and if there's someone in the chat, you guys might need to tell me again, because I can't have my MATLAB script kind of like full screen, and I can't have the chat open up at the same time. Yeah. Let me actually look at this again. All right, I got it. Okay, so first thing we're going to do, again, we have a script open up, and we're going to just basically write a bit for our script here. So don't ask why I have that title, weak hosting. It doesn't really even make sense for what we're doing. So first thing we're going to do is we're going to assign some of our knowns for the system here. So you can look at the handout if you want. That does kind of show the steps that we're going to take for the experiment today. But I also write this down kind of step by step in our slides here. So the first thing we're going to do is define some of our knowns for our system. And then we're going to make the first open loop system in Simulink. All right, so let's make some really nice comments here. EGME 476A, lab 3, control system tuning. Okay. And then we're going to clear the memory. So let's do clear and then CLC. I got to make a comment. I just got to. Oh, oops, not yet. Okay, so now we're going to have a new section here for defining our knowns. And so if we look at our slide right here, we see that we have our knowns right here. So basically J, B, and A, they're just kind of given parameters for our system that relate to the actuator mechanics that we're going to have for the airplane, and then some of the roll dynamics that we have. So these are just given inputs that we have for our system that are going to be able to read the error that we have. And once we get to a closed loop system, especially, read the error that we have, and then they're going to do some stuff, and then we can look at our output for the airplane. Okay, so let's define them. So the first thing we have is J, capital J, and that's 3 times 10 to the 5th. And we can put in what our units are. So we have Newton times meter times second squared. Okay, then we have B, which is equal to 2.5 times 10 to the 5th. So 2.5 E5. Let's make another comment here, and this will be Newton meters times second. And then we have A, that's equal to 2 times 10 to the 6. So 2E6. And then we have our units of Newton meter, and this will be divided by degrees. Okay, and then instead of, actually, I'm going to leave it like that. So I'm going to put T underscore 1 equals 8 times 10 to the 5th, and that's going to be newtons. All right, so this part is a bit more relevant to us. So T1, that's going to be our noise disturbance on the system. So this is basically the bird strike. So the bird is going to strike our plane at 8 times 10 to the 5th newtons. So this is for the first one. This will be for the closed loop system, and later on for the did I say closed? I don't know. This is for the open loop system, and later on for the closed loop system, we're going to have a new value T2, which is going to be T1 times 2. So that bird strike is going to be twice as hard. All right, so there we go. We have our knowns there. Okay, and then I'm going to make a little section here. So to make a section in MATLAB, we put 2% signs, and we'll do open loop simulations. All right, so this is, we don't have much code for this experiment. We're going to add a bit more, but right now we can run it, and we're just going to save this file. Name it whatever you want. You do need to, MATLAB has some kind of predefined syntax kind of rules that they have for saving a file. I think it needs to start with a letter, and you can't have any spaces, stuff like that. So if you see an error, then you probably saved the file with the wrong kind of syntax. So, and to run it, you can go to editor and then run, or you could just press F5. Okay, so there we go. Well, my workspace over here. I don't know if it's going to go well. Yeah, I'll leave it like that. Actually, I can... I'm not going to mess with it now. It's moving these windows around is a little weird on my computer. See where it kind of shifts weird. There we go. That's how I want it. All right. All right, so now we're going to open up Simulink. So you can either go to the Home tab and click on Simulink up top here, or you can just type in Simulink in the command window, and it's going to open up. It might take, a few seconds. All right, let's create a model. A blank model. And wait 10 years. Cool. All right, so this is right here on our slides. This is going to be the first model that we make inside of Simulink. So this is an open loop system. So what we have here is our input roll angle that we're going to specify for the aircraft. And once we input that, our actuator is going to do some stuff to basically adjust our ailerons, if I'm saying it right again, and that's going to basically create a torque on the aircraft so we can have a roll. And then we have our roll dynamics transfer function as well. So these two blocks here, they're going to be transfer functions inside of Simulink, and then we can view our response. Okay, so let's just make the kind of skeleton right now for this system here. So we can click on a library browser, and then we can select our blocks, but I'm not even going to keep that open this time because I never actually use that. I just kind of type stuff in. So the first thing we're going to do, we're going to click on this canvas here, left click, and then we're going to type step, and then we're going to press enter, and then we're going to get a step function here. Okay, let's rename this. So I'm going to just click on the block, double click on this text here, and I'm going to call this input roll, just so I know that this is going to be the input roll angle that we have on the system. And now let's add in our transfer functions that we're going to have for our system. So I'm going to left click again, and then I'm going to type in transfer, and then you'll see up top here, the first kind of option that we have is transfer function. So if you're getting this block from the library browser, that's going to be under the continuous kind of library that we have. So I'm going to press enter. I guess I could show it. So we're under a Simulink and then continuous, and then there's transfer function right there. Okay, so there we go. We got one transfer function. And now I'm going to go over this block. I'm going to right click and drag to make a new transfer function. And then let's add in our scopes as well. So I'm going to left click, type in scope. There we go. And this is going to allow us to look at the output. Wow, that was laggy. It's going to allow us to look at our specified output for anything that we want to look at. So we're going to have two of these. Okay, so there we go. Let's rename some stuff here just so we can keep everything organized. So this will be our actuator. And this one is going to be our roll dynamics. And then let's rename our scope here for aircraft response. And this scope down here, we're going to call this one input roll scope. So all this is going to do, this one here, we're just looking at our input for the roll angle. So it's not going to be an exciting graph at all. Okay, so there we go. And now we got to basically edit all of our blocks here so we can actually simulate the system correctly. So you see here, I have this little note here. So we can see in our actuator block what we're going to put down for the transfer function. That's going to be a divided by s plus 0.1. And then for our Roll dynamics, that's going to be, it doesn't show it actually in the transfer function once we input it. It might on your computer, Simulink, it kind of varies for how it displays stuff for different kind of operating systems, but that transfer function is going to be 1 divided by s multiplied by js plus b. So we're not going to actually go through the derivation for kind of an equivalent time domain representation for this transfer function. But this is a given kind of parameter for our system. So if I open up our lab handout, so there's a lot of theory in the beginning. So this is what we have here. So we have our givens J, B, and A. And then these are our transfer functions that we're going to model inside of Simulink. All right, so let's go back to Simulink. And let's start adjusting stuff. So the first one that we're going to adjust is our actuator here. And just want to be sure, yeah, that's going to be A divided by S plus 0.1. So let's actually go back to our handout. So this transfer function, it's relating our output W to our input, which is our input roll angle, theta. And that's going to be equal to this transfer function, A divided by S plus 0.1. Okay, so I'm going to double click on our block here for the actuator. And then you'll see by default, Simulink shows our numerator and our denominator, and everything that we want to specify for the numerator and denominator should be inside of brackets. So by default, they're all ones, but we're going to change this. We're going to change the numerator to a capital A. That's going to correspond to one of the knowns that we defined in our script. And then we're going to change our denominator here. So we're going to have a 1 and then a 0.1. So this is going to correspond to S plus 0.1. So to kind of explain this a bit, I guess I'm explaining for the next one, but what we have here, did I not put this in the slides? Maybe not. Oh, I did. Okay, so we, on the denominator, we basically have a first order polynomial, which is s plus 0.1. So you can kind of think of that like some linear function like 5x plus 1, whatever. So in MATLAB, if we're going to kind of define that polynomial, we need to write the coefficient for each term. So in this case, since we have a transfer function, by default, that's going to be a transfer function of 1 divided by s, but in our case, we have s, so that's just going to be a 1 in our denominator. And then we also have 0.1, so we're going to specify 0.1. Okay, so in the numerator, we change that to A, because that's one of our knowns in the system. And then in the denominator, by default, we have 1 and 1, and we're going to change that to 1 plus, or just 1, and then a space, 0.1. Okay, if that doesn't make too much sense yet, maybe once we get to the next one, it'll kind of clear it up a bit more. All right, so we're going to click apply and then OK. And then you see our box here kind of updated to show us what we have. All right, for our roll dynamics now, that's going to relate to our output, which is going to be the aircraft response. So our final roll angle that we have on the system, to our input, which in this case on this kind of left side here is going to be C. All right, so the transfer function that we need to model is 1 divided by S multiplied by J times S plus B. So if we kind of, do some multiplication here, we have a denominator of S squared J plus SB. All right, so now we have basically a second order or second degree polynomial. So, if we're just looking at it like S squared J plus SB, if we just put in J and B for our denominator here, that wouldn't work. So remember MATLAB, we need to specify all of the coefficients for our polynomial. Since this is a second degree polynomial, we basically have to specify 3 terms. Okay, because in this case we have s squared j plus sb, and technically our third term is a 0. Don't put this. Gee, I made these slides pretty late last night, so blame it on my ability to think, but I couldn't really think, I guess. Don't put an A here. That should be a 1. I'm gonna write a note so I can change this later. Okay, so yeah, don't put an A. It's actually going to be 1. If we go back to our handout here, we can see that transfer function is 1 divided by s multiplied by js plus b. So in our numerator, we can leave that as a 1. I actually remember last night when I was kind of going through this experiment, just to make sure that everything was kind of, correct. I remember running this kind of simulation here, and it was wrong. And I was going crazy for why it was wrong, but it was because I had an A for the numerator and not a 1. Okay, and then for our denominator, again, we're representing the second degree polynomial. So we're going to put j, that'll correspond to s squared j, and we're going to put a b, that's going to correspond to s times b. And then we have to put in our third term, that's going to be a 0, because technically we have a third term, which is 0. All right, so the numerator, that's 1, denominator is j, b, and 0. And make sure that you have a space between each term here. We'll click apply, and then OK. So on my screen, now it just shows numerator and denominator for the block, but of course, if I double click on it, it's a 1 for the numerator and denominator, j, b, 0. All right. Gotta make these evenly spaced for my, I don't really want to say OCD, but whatever. All right, so step 1, let's do the first step that we have to do for our kind of simulations here. So if I go back to the handout and I scroll down a bit, we see for our open loop system, we're going to be modeling 2 systems. So the first one, we have a disturbance torque input of 0. So our bird is going to smack the plane at 8 times 10 to the 5th newtons, and from that impact force, that's going to create a torque on the system. So our plane is kind of start to roll a bit. And then we're going to use an input roll angle of 1 degree. And then we'll look at the response, and you're going to discuss it in your report. Okay, so first thing we're going to do, we got to change our input angle here. So we're modeling our input angle as a step function. So if I double click on it, we have 3 kind of arguments that we can change here. So step time, initial value, and final value. So step time, this is going to be when our step function occurs. So by default, our step function is going to occur at a time of 1 second. Our initial value is 0, and our final value is 1. Now that's by default. Let's hook this up to a block. Yeah, okay. So I'm going to click on this block here, and because I want to make everything look nice, I'm going to press Control R, and that's going to rotate our block. So now you see that my block here has this kind of node hanging up top. And then I'm going to click and drag our text so I can put that down there. Of course, you don't have to do this. I just want to make it look a bit better. I'm going to click Save. Now this will bring up what we need to save our simulation file as. So I'll call this, just open underscore loop. underscore class. All right, I'm going to save that. I'm going to change our simulation time up top here. So where it says stop time, and of course we're under the simulation tab. I'm going to change that to 450 seconds. All right, so that's what we're going to run all of our simulations at. So 450 up top. And then I'm going to click on modeling, model settings. And then we're going to change, instead of a variable step size, so we changed this before in the past lab, I'm going to change it to a fixed step. And then I'm going to make that fixed step size 0.01. And this is to allow us to have a very small step size, so our graphs are going to be nice and smooth. All right, so we did all that. Now I'm going to run our simulation here by clicking on run. And now I can look at our output here. Or maybe I shouldn't say that. I'm going to look at what our input roll angle looks like. So I'm going to double click on the scope block. And here we go. So I'll change the time for now because just so we can better see this. All right, here we go. So this is now running for 10 seconds and we can see our step function. The initial value is 0. Once we get to 1 second, so that was our step time right here. Once we get to 1 second, we're going to shoot on up to a final value of 1. And then it's going to stay at that value forever. Okay, so what we have to do though, we have an input angle of 1 degree. So we need to change this so it's just going to start out at 1 degree and not have a value of 1 degree starting at 1 second. So we're going to change our step time to 0. And then we have our initial value 0, and then our final value is 1. Click apply, okay, run it. Look at it. Beautiful graph. We have a value of 1 for the entire time. All right, so I just want to make sure everyone's following along so far. So put a yay or nay in the chat if you're good so far. Cool. All yays. One ye. One heat. Okay. All right, so we got that. Okay. Oh yeah, I even show it here. So step time of 0, initial value of 0, final value of 1. All right, so now we can run our system. So first we need to connect everything. So I'm just gonna click and drag all these kind of nodal points here. We'll do that. Then I'll click save. And then I can run our system. So we're gonna do that for 450 seconds. We'll press run. And then we'll look at our response here. All right, so this is our response, of course, in Simulink here on the left. And then for the slides, I wrote some code to automatically simulate this simulation here in Simulink, and then it can make a plot automatically by itself. So this is the same plot, but we have one, again, just one of them is plotting automatically in MATLAB. It looks a bit better than the plot here in Simulink. Okay, so if we're looking at this, you're going to discuss this in your report. So we had an input roll angle of 1 degree, and then we ran our simulation for a time of 450 seconds. And then, wow, look at this output. Where if you look over here for whole numbers, we're at 35,000 degrees. So our plane has rolled quite a lot. So obviously this is not a stable system, and it's nowhere near what we want to have for our output. So we're going to have to do some stuff. Basically, we're going to need to have a closed loop system. So we can evaluate our error, which is ginormous here, and then we can act on the error to have a better response. Okay, so let's actually go back to MATLAB now. And we're going to add on some code here so we can make this plot automatically for us. Okay, so we have a section called Open Loop Simulations. I might check what I have. Okay, so our first one here, we're going to do, we'll just call it open loop underscore sim. So we're going to assign a variable, and then we're going to simulate our Simulink setup that we just had. So I'm going to do sim. And now here I need to put in the name of our simulation file. So, we got to be sure that our script and our Simulink file are in the same folder. We can see that over here. So our Simulink file in my case is open underscore loop underscore class. And then .slx, we got to put our file extension. Okay, and then I'm going to suppress the output so I don't see the text down here. Okay, and then now if I run this, it ran. So it just did the simulation. And over here in the workspace, we can see our name. So we see all of our variables, and let me resize this. Okay, and then we have open underscore loop underscore sim. That's the variable that we assigned to this to us running our simulation for Simulink. So if I double click on that, then we see we have T-out, simulation metadata, error message. So there's not really an error here. That's just, it's storing that automatically in case there is an error. Simulation metadata, who cares? T-out, so that's just going to show us our time right now. So we want to see some more stuff though, right? We want to see the output roll angle that we have so we can plot it. All right. So I'm going to close out of that. And we're going to go back to Simulink right now because we need to add something. Okay, so do I not show it here? I guess I don't. We need to add this two workspace blocks. So we want to have our output, which is right here. And then we want to take that to our workspace for MATLAB. So I'm going to left click and type to space workspace. And if you're in the library browser, that's under Simulink and then syncs. Press enter, and then here we go. We have our two workspace block. I'm going to connect it to the output of our system. And sure, I can rename this to aircraft output. If I was going to try to do aircraft response, that's not going to work because I already have this scope block called aircraft response. So I'll do aircraft output. Of course, these are really the same thing, but the scope is just letting us look at the output already inside of Simulink. While our two workspace block, that's going to actually create a workspace variable inside of our MATLAB script. All right, so I'm going to double click on this and I'm going to change some parameters. I'm going to change our variable name here to, I'll call it response. And I think last time for the first lab, I changed in the video that I made after class, I changed the save format to an array. So you can do that, but I'm actually going to leave it right now as a time series because we can actually more easily plot this if we leave it as a time series in MATLAB. We don't need to type as much. Okay, so variable name response, we're going to keep this part the same. Destination is the same. Save format is also the same, just a time series. Click apply and then okay. And then save it. Okay, make sure you save it. And then we'll go back to MATLAB here. And I'm going to run our script. Okay, and then I'll look at our workspace again. So I'm going to double click on that. And now you see we have a new kind of entry here, which is called response. If I double click on that, let's make this a bit better. Okay, so double clicking on that, then we see that we have this time series. So we have our time, which we used is a fixed step interval of 0.01. And then data, that's going to correspond to our output rolling goal for the system. Okay, let's make this bigger again. All right, so now we're going to add some code to make our plots so they look better than what we have in Simulink. All right, so I'm going to make a new section here called Open Loop Plots. And then we're going to make a plot, right? So we're going to do plot open underscore loop underscore sim. That's our variable here that we assigned into MATLAB to run our simulation for Simulink. And then I think I need to use dot notation. Yeah. Okay, so we have to use dot notation, which is, we also did this for the first lab, but when you took the MATLAB class 205, you might not be too familiar with it, but we're going to use dot notation for this. So we're going to do dottout. So this is going to look at our workspace variable here, open loop sim, and then it's going to access this value right here, tout. So I could choose tout here, or I could actually go into our time series data and specify the time right there. But in my case, I didn't do that. So that's okay though. It doesn't matter how you do it. It's going to be the same time. Okay, so that's our X data. Now we need to have our Y data. I think I actually plotted this a little different in the end here. Yeah, let's do this. So, here I was specifying our X data and then our Y data, but we can do this even easier by accessing our time series data. So I'm going to put dot response. So I have open loop sim. That's the variable here. And if I go into the workspace and double click on that, so what we were doing is we were accessing this array here for tout. Instead, I can just access this time series here for response. Then I can plot all of this right away. So all I have to do is open loop sim dot response. And now if I run this, then look at that. We already have our plot. I didn't have to specify our X data and the Y data. It did it automatically because we have a time series kind of array. All right, and then, by default, they give you a title name and an X label and a Y label. I'm going to change this to make it look a bit better. So line width of 2. And I guess I'll make a title as well. Title, open loop, response. And then we're going to specify for theta I. So theta I, that's our input roll angle. And that was, what was that, 1? I think it was 1. So we're going to do for, I have to do a backslash here to get our theta symbol, theta underscore I. To get a subscript, we use our little underscore here. And now that's a 1 degree. So MATLAB is nice and weird for the formatting. So I have to end our apostrophe here. And I'm looking where I have it here. Yeah. We're going to put in char for a character. And what is it? 176. 176. And then we have to wrap all of these in brackets. Okay, so we put a bracket over here and a bracket over here, and then we close it out. I know that's a bit weird, so you might need to look at that again. And this is not formatted correctly. For theta I, what's wrong? All right, I'm not going to spend a lot of time on this, but I had our plot working correctly last night. So there might be an issue because this notation here, this is what you do if you were putting in LaTeX code. Now I thought they also did it kind of on their own. So maybe not. So I'll look at this later. It's just to get our formatting correct. But so for now, I'm just gonna change this bit like this. I need to put this in the inside here. Okay, I'm not gonna spend too much time, but here, let's do this. Theta I equals 1 degree. And then I'm gonna put interpreter, LaTeX. I might need to change where I have the dollar signs. Can't remember off the top of my head. It looks like we are gonna have to change that. Yeah. So we'll put them inside. So our dollar signs for LaTeX code, that just means it's something for math. So let's actually put it over here. Theta I equals 1 degree. All right, now I run it. So we have our good formatting for theta I. And LaTeX, they're also pretty great. And by that I mean they have an annoying thing here where I can't just do \degree unless I have some package for LaTeX. So I think if you are using LaTeX, so the package for that is called GenSymb, standing for general symbol. So you would have to use that. And then you could do a \degree. But MATLAB, you can use LaTeX packages, but it's hard to install them, apparently. So I'm just going to leave this like this for now. And we'll worry about the formatting a bit later. Okay, there we go. So kind of a little detour there. Okay, so we got our plot, and now let's go on to the next step for our experiment, which is step 2. So already an hour in. So step 2, we got to model the bird striking our plane. Let's go back to our Simulink model. And now we're just going to, you can actually save this file now if you want. But what I'm going to do, I'm just going to change some parameters in here. So yeah, I'm just going to have one open loop Simulink file and one closed loop file. But in this case, for the report, what you'd want to do right now is you would run your code and then save your figure so you can talk about that in your report. All right, so here I'm just going to change some stuff though. So we're going to change our input roll angle. So this time, instead of an input roll angle of 1, we have an input roll angle of 0. So I'm going to put all of these to 0, click apply. If I was going to run this right now and I look at the output for the roll angle, that's 0. And then we're going to add a disturbance to our system, which is going to be the bird strike. I also need to change this leg too. You can do it how I have it listed here, but okay, I'll just get to it once we get to it. Okay, so we're going to add our disturbance here, which is again going to be a bird strike. And we're going to model this as a step function as well, as a summation of 2 step functions. So let's get our step function here. Left click, type step. All right, here's our step function. And then we're going to copy and paste. Now we have our 2 step functions. And our disturbance is going to occur after our actuator. So, we have our input roll angle. Our actuator is going to try to have that input roll angle that we just prescribed to the system. And now we're going to have our bird strike that's going to now affect the response for the system. And then we're going to have our roll dynamics here. And then we're going to see what that output is going to look like. All right, so for our first step function here, we're going to change our parameters. So if we look at the handout here, we see that our bird strike is going to occur at a time of 1 second to 1.1 second. And the value is going to be a step function where the value is 8 times 10 to the 5th. So in MATLAB, we call it that t_1 for one of our defined variables. All right, so our first step function here, our step time is going to be 1 because I want this to occur at a time of 1 second. The initial value is going to be 0 because we don't want, we don't want a value when we're already starting our simulation here. Then our final value is going to be t_1. I click apply and OK. Just making sure I called that t_1, which I did. Okay, so that's one part. Let's actually get a scope block here. So I'm going to right click and drag. I'm going to call this birdie. And if I was just going to look at this right now, let's do that. So I'm going to run it, look at this output. And, we're running for 450 seconds, so our input is really smushed over to the left here, but this is occurring at a time of 1 second, and then we go up to 8 times 10 to the 5th newtons. So I'm going to change our time domain right now to 10 seconds, just so we can see it better. And there we go. So we start at 0, we get to 1 second. We have our bird strike. We go to 8 times 10 to the 5th newtons. And because I left the final time as 8 times 10 to the 5th newtons, that's where we stay. So I need to change this, though, to go back down to 0, because really this is an impact force. So it's only going to show up for, a fraction of a second. So we're going to use another step function. Okay, so in my slides, what I did is, well, first let's set our step time. This is going to be not 1 second, but 1.1 seconds now, because this is going to occur. We have our first step function here at 1 second, and our second step function we're putting in, that's going to be at 1.1 seconds. Okay, so that's why we put 1.1, and our initial value is actually going to be 0 here. It's going to be 0 because we're going to sum our step functions here. So this initial value is relative to the summation of our step function up here. So we're going to put that as 0. Okay, so at this part, you can do what I have in the slides, which is putting our final value to negative t1. But in my case, I'm actually just going to leave this as t_1. Then I'm going to click apply and then OK. So the difference here, so my slides, I prescribed it as negative t_1. And then when I do a summation of our blocks, I'll actually do this first. Okay, so I'm going to put our final time as negative t1. I'll click apply. Okay, now we need a summation, so I'm going to put sum. Also, you'll see here our step sign, or step function, it changed in direction because now it knows that I have a negative sign here. If I sum these right now, and then I connect it to our output, I'm going to run this, and then I'm going to look at it. And there we go. So we have our step function that's modeled correctly. But again, what I'm going to do is I'm going to change this to a final time of t_1. I'm going to click apply, click OK, and now you see our step function. It shows it as a positive value once again, which is what I have in the model here. So I don't want to confuse you, right? So let me try to explain. So in this slide right here, for our second step function, I put a final value of negative t1. That should say t1. Because if I go to the model, that's how I modeled it here, where there's step function, where both of these step functions had a final value of t1. Now the difference is I'm going to change our summation block. Before I do that, I'm going to run this now. And now you see that this is wrong, right? So I'm adding step functions now. So my first step function, it starts at 1, it goes to 8 times 10 to the 5th. And as I have the second step function right now is starting at a time of 1.1 seconds, and then the final value is t1. Now, of course, our initial value is relative to the summation here, right? So it's starting at 1.1, it's going up to 8 times 10 to the fifth again. So I just need to change this to a negative sign for our summation block. All right, so now you see we have this step function, and now we're just essentially going to subtract that step function. So now if I run it, and I click on Birdie, and there we go, we have our step function that's modeled correctly. So we're just modeling the same step function at a different time, right? And we're just subtracting it, so we get this this output here. So if I did a terrible job explaining all that, you can just look at this right now. Our first step function has a step time of 1. We want to start at 1 second. Initial value of 0 and a final value of t underscore 1. And then our second step function, a step time of 1.1 seconds. We want that to start then. And initial value is 0 because it's relative to our first step function. Then a final value of t underscore 1. And what I'm doing here is I'm using a summation block, so I have a positive sign for the first one and a negative sign for the second one, so I can subtract them. And then we get our correct output. Okay, so let's change our total simulation time again to 450 seconds. And then I'm going to add a label down here. So I left click and I just start typing. And I'm going to do bird strike. And then it shows create bird strike annotation. Press enter. And there we go, just so we know what we're looking at here. Okay, now we need to add this to our system. So we're going to add this again after our actuator. Okay, so let's drag this just up like this. Oh yeah, we need a summation block up here. That's why. Okay, so we need another summation block to correctly incorporate our bird strike. So there we go. And we'll just connect them all again. And if I want to look at our output for the bird strike, I can just connect that right there. Oops. I'll drag you up. There we go. All right, and now I'm going to save it. And then I'll run it. And then we should see a graph that looks like this. So we'll look at the response. And we have that same graph. All right, so good. So if we look at this graph, at a time very early on, because of our bird strike, let's go back a bit. So our input roll equal was 0, and then at a time of 1 second, we had our bird strike. So then our output launches up relative to 0. It launches up to around like 0.32 degrees for the output roll angle for the system. So, you know, this isn't bad, right? It's not that far off, but technically our error is going to be infinite here because our prescribed input roll angle was 0 and our output roll angle is 0.32, and it's staying like that forever because we have an open loop system. Okay, so let's close out of that. Let's go back to MATLAB here, and we want to add in this plot. So let's do, actually it's going to do this right now for us because, you know, I only have one file here. So I'm going to have to change this. This is why I said to save your first figure before. So I'm going to change our title to theta1 equals 0, 0 degrees, and then we'll just put in bird strike. Make your title better than this, but if I run the code now, as you see, our graph has now updated to that corresponding simulation that we just ran. Okay, so if you want to kind of look at all your plots at once in MATLAB, then you will have to save multiple Simulink files. Okay, so there we go. All right, so let's analyze this response. This will be, you know, a good part of your analysis here for your lab memo. you're going to have to analyze the response for, we have 5 different things here. So the first one that we have is peak response, and this is going to correspond to the maximum value of our response. Right, so here for this graph, again, this is an open loop system, so our max response here is going to be 0.32. Our peak time, that's going to be the time it takes to get to our peak response or our maximum response. So here, that's going to be like 1 second. Actually, I guess not 1 second, because we're going to have the bird strike, and then our roll angle is going to continue to increase because that bird strike has induced a torque on the system. So we're going to find the peak time. So for all of this, this is when those toolboxes are going to come to play. So I'll show you how to do that in a second. Okay, so peak time it takes to get to our peak response, and then our overshoot percentage. That's going to be a percent overshoot from our input. In this case, our input was 0 degrees. Our output here is 0.32. So you're just going to calculate that percent overshoot, or that kind of percent error that we have for this response. So you can see I have that kind of calculation down here. Our overshoot percentage is our actual overshoot minus what the input should be, which is 0, and then we're calculating that kind of percent kind of error. All right, settling time. So this I'll probably accept basically for when your system reaches steady state. Technically, settling time is the actual time value when your system stays for the rest of the time, when it stays to within 2% of your input value. So I didn't have time to try to figure out how to do this in MATLAB or with our toolboxes. I'm sure there is a way. So for sake of simplicity, I'll say for the lab, you can see that your settling time is just the time to when steady state is achieved. Technically, that's not true though. Settling time is the time value that we have when we stay within 2% of the input value. So again, I'll try to be clear on this for the deliverables for what I expect. All right, and then steady state error, that's going to be the degree difference. So the actual difference that we have for our output degree and our input at steady state. So here we reach steady state actually pretty early on. So you're going to look at that steady state error. So of course, in this case, it's going to be an infinity once again because our input angle was 0. Okay, so that's what you're going to do. So how do we find some of this stuff? We're going to use, where do I have them here? I know I put this in. Okay, here we are. It's related to this. So, at some point we're going to be finding T star. And so I have some pictures here that show our toolboxes, but we're going to actually do this right now. Okay, so we're going to go back to Simulink. And now what I'm going to do is well, I don't have to run it again, but we're going to click on our aircraft response here. And if you installed those toolboxes before we started today, looking at your Simulink output here, you can go to Tools, Measurements, and then we're first going to click on, we'll do Signal Statistics. All right, so we click on that, and then this box is going to show up here on the right-hand side. So again, to go there, we're looking at our graph here. We go to Tools, Measurements, Signal Statistics. Okay. So this is going to give us some good stuff that'll help us get some of these parameters here. Okay, so peak response, right? That's our maximum value. Well, this toolbox, it does it automatically for us. It shows our maximum value is 3.2 times 10 to the negative 1, or just 0.32 degrees. So we put that down as our peak response. How long did it take to get there? it also shows us that in here. It's 39.85 seconds. So we would write that down. I guess I put 8.6 here, really 8.5. So that's how long it took for us to get to our maximum value of 0.32 degrees. Okay, and then if we go to tools and measurements and bi-level measurements, we can click on that. And so this will be a little more relevant once we get to the closed loop system. But this will also be able to show us some stuff. So let's go out of transitions. Let's click on overshoot and undershoot. So here it can show our overshoot percentage. So it shows us that, and they have a parameter here for settling time. Now, I haven't got this to work. You might need to prescribe basically some explicit input here for what it should be, and then it can maybe look at that. So again, I'm gonna look into it, but as of right now, for your lab report for settling time, you can just say that that's going to be the time it takes to get to steady state, and kind of make a little comment that that's not really the settling time. Okay, so this gives us just some more stuff we can look at. Now, if you don't have this, the toolbox is installed, you could still kind of look at some of this stuff basically manually. I'm going to make this full screen. That is not full screen. There we go. So we can do this kind of manually by going to Tools, Measurements, and then Cursor Measurements. We'll click on that. And now we have these two little data points that we can move around. So what I'm going to do, I'm going to move this first one to the beginning. So what I'm going to try to find right now is our peak response and the time to the peak response. So the first one is moved over all the way to the origin, and I can move the second one around. And I can try to find, well, we know right now we're at the maximum value here. So if I look on our cursor measurements, and 2, because we're in the second one, it shows our current value is 3.2. So as I move this around, you can see our corresponding time is changing, right? But our value is the same, and that's, in this case, our peak value. Okay, so now what I'm going to do, I'm going to drag this to the left, and I'm going to keep an eye on our value column here and see when that changes from 3.2. And again, this is to try to find our peak time or our time to the peak response for the system. So yeah, why is it like this right now? There's something I'm missing here. I remember doing this last night. Yeah, okay, there we go. Maybe not quite yet. Do I need to change this over here? Yeah, there we go. Okay, so what I basically had to do, I had to drag our first kind of data point over here, because what I'm looking at right now is delta y, our change and our value here. So I want to find when that's 0. And once it's not 0, that's going to be right around when our peak time is. Maybe I solved this backwards. So if I go to 39.85 seconds, already way past that. Oh, no, I'm not. Okay, 39. So you see our delta y, it keeps decreasing and decreasing here. So even though our y value here, there's just not enough significant digits to show that our value is changing, but technically it is. So that's why I'm looking at delta y. So we're still decreasing here. Still decreasing. And you see our time right now is 38.9 seconds. And it just went to 0. You saw that delta y right here. This value just went to 0. So let's go back a little more. And we're going to try to get it right when it goes to 0. Right, there we are. So this shows 40 seconds now. as we move this cursor, we can't be totally accurate with it. So, doing this manually isn't really the best way. So, okay, there we go. So yeah, I can only get it to 40.2 seconds, but with our toolbox, with our signal processing toolbox, it did this automatically for us. So it said that our max response or peak response is 3.2 or 0.32 degrees. And the time to our peak response was 39.85 seconds. While if we did this manually, the time to our peak response was 40.228 seconds. All right, so there's a little difference there, but that's why I would recommend that you get the toolbox so you don't need to do all of this kind of stuff yourself. Okay, so we're done with this part now. So we'll close out of that. And now we're going to go on to our closed system response. Okay, so the first thing that we have to do, if you can remember, we need to add a proportional controller now, and also have our kind of sensor at the bottom of our system that's going to read the output that we have. And we're going to start implementing our Ziegler-Nichols rules. So we're going to put in our proportional controller, set it to 0, and start to increase it until we get a marginally stable system. So this is what our closed system is going to look like. So we're going to assemble this right now in Simulink. And to start our tuning of our controller, we're going to first set KD, our proportional controller here, to 0. Because we just want to tune our proportional controller until we're marginally stable. I think my dog's whining. Okay, so what I'm going to do now is I'm going to copy our Simulink file here because I'm going to make a new one for our closed system. So we have open loop underscore class in my case. I'm going to copy that and paste it. And now I'm going to rename this to closed loop. So closed loop class. Okay, I'm going to close out of our open loop simulation here because we don't need that anymore. Yeah, sure, I'll save it for the last thing I did. And then I'm going to open up our, our copy and pasted file here for the closed loop system. And now we're gonna change this so we can build our closed loop system. All right, so let's do that. Okay, so I set this up a bit differently in my slides, but I'm actually gonna kind of build up our complete closed loop system right now. So I'm actually gonna skip ahead to when I did that just so I can reference that. I really didn't input that slide. All right, I'll add that as well. So there's some stuff I forgot to input. All right, so yeah, I don't have it. All right, I can just look at my laptop though. Just want to make sure I set everything up correctly. All right. Trying to think what's the best way to first start it out. Okay, so let's do this. I'm gonna move this over. Then I'm gonna move our input scope lock. I'm gonna move it up top here. Of course, that looks terrible. So I have to. I'm gonna do Control I to flip it. So now that looks like that. And then what we're going to do is we're going to add a summation block over here. So summation, delete this. And we're going to put our summation block right here. And this is going to calculate the error. So if you remember from some previous slides, we said that the error for our system was going to be our input subtracted. We're going to do our input subtract or minus our output. So our error is going to be equal to our input here minus this output over here. So let's change our summation block to a minus sign at the end here. Okay, there we go. And then we're going to, let's move this up a bit. I'll tidy this all up as we go. We're going to add in our kind of sensor at the bottom here. That's going to measure, measure the output. So if you remember from our past slides, we said that this kind of sensor was just going to be a simple gain. So it's going to be a gain block that has a value of 1. So let's type in gain. Then I'm going to do Control I so I can flip it. And I'm going to connect this to our output here. You know, it doesn't matter if I put this here or here. Let's just put it right there so it looks better. And then this is going to connect to our summation block right here. Again, this summation block is calculating the error. So let's click and drag this text, move it up top. And I'm going to call this error. All right, there we go. Now I'm going to save this file just so we don't lose it. And then I'm going to rename this gain block down here to output sensor. Okay. And now we're going to actually add in our PD controller, so our proportional derivative controller. Okay, so this is going to occur before our actuator, because what we're doing here is we have our input, our actuator right now, it's going to do something. Then we're going to get our output here, and our sensor here is going to read that output. Now we go over here, we're going to calculate the error. And now that we calculate the error, now I want to implement our PD controller. So our PD controller can look at that error. It can decide, it can do our computations with our proportional gain for the proportional part. And it can differentiate the error with our derivative controller. And then it can tell the system what adjustments it needs to make. And it'll send that signal to our actuator. So the actuator can actually implement those adjustments to our system, and we can have a better output response for our specified input. All right, so let's add in our controller. So I'm going to move all of this stuff over to the right just so we have some room. And then we're going to add in our proportional controller. So that's just going to be a gain. So here we go. Here's our little gain block. And then I'm actually going to rename this to KP. And then we'll do prop controller, so proportional controller. All right, and now let's add in our derivative controller. So we need to first import a derivative block. So I'm going to type in derivative %. There we go. And then we're going to have another gain block. That's going to be attached to our derivative. And basically, the kind of summation of this stuff here is going to, well, not the summation, but our gain block multiplied by our differential block, that's going to be our derivative controller. So I'm going to rename this gain block to KD. And I'll make a little annotation up here called derivative controller. I didn't press enter. Derivative controller. There we go. And now we're going to connect these first to this summation right here. That summation block. Just like this. So they're going to kind of act in parallel to make our proportional derivative controller. And now I need another summation block over here. Okay. And a pet peeve of Simulink, I can't manipulate this summation block to where I have a node up here. It really bothers me. You know, I can't move this like that. Even if you rotate this with Control R, it doesn't work out well. So whatever, we're gonna leave it like this right now. All right, so there we go. This is going to be our closed loop system now. So we're going to have some input. Let's pretend we're starting, right? So we have our input. So there's no error to act on yet. So we're not going to be doing anything. We are going to have some proportional gain here for our KP controller. So something will be done right here. And then that's going to send our signal to our actuator. The actuator is going to act on our controller. And then we may or may not have a bird strike. And then we're going to have a roll dynamics. So again, that's another transfer function that's going to take into account what we have here and what we have from our actuator. And then we're going to have our aircraft response. Our output sensor is going to read what our output was. In this case, we don't want to, modify what our output was. So we just have a simple gain. We're just multiplying by 1 to look at that output. And that's going to go back here to our summation block where we calculate the error by looking at our input, subtract it by the output, find the error value, and now we can use both the proportional controller and the derivative controller, because now the derivative controller can differentiate the error that it just calculated. And then that's going to send a signal to our actuator, which can then, act on that signal, and then we can start to improve our response over time. So the output angle is going to be closer and closer to our input angle. All right, so let's start doing some stuff. So the first thing that we have to do is tune our proportional controller, and so we get a marginally stable system. I need to change some things here. So for our derivative gain right here, KD, I'm going to change that value to KD. Nope, not this. KD. All right, click apply. Right now I have an error because I didn't assign or specify that variable in our script yet. So we're going to do that as well. And then for our proportional controller, let's double click on that and change this to KP. Click apply. We don't have a value for that yet, so we're going to get to that. I'm going to click save. I'll go to our MATLAB script. Open it up here. And what we're going to do now is define our knowns for KP and KD. I'm going to see when I actually put that in our script. Okay. Okay, so I'm going to do that down here. So I'm going to make a new section here. And we're going to call this closed loop simulations. Maybe I could format all this better, but it's okay. Make a little comment here, define our knowns. And this is one we're going to put in our values for KP and KD. So let's do KP. So first off, we're going to start at 0. Remember, we need to tune our controller. Starting from 0, increase until it's marginally stable. And we'll have KD. Right now, that's going to be 0 as well. So we first want to start out by tuning only the proportional controller. Okay, and then below this, what I'm going to do is then I'm going to run the simulation for that Simulink model that we just made for the closed system. Okay, so I'm just going to call this, we'll put in a comment here. I guess we'll make a section just to be consistent with what we have above. So closed loop simulations, and then we're gonna call this closed loop sim equals sim, and then again we need to put in our file name for our simulation, and that was called closed loop class.slx. Let's just be sure. Closed loop class.xls, or not XLS, I'm thinking of Excel. I was thinking XLSX, that's an Excel file. Okay, so .slx, there we go. Close that out, put a semicolon to suppress it. Now if I run the script by pressing F5, Let's comment out this plot. I don't need you. Okay, we can run our system. Now we go back to Simulink here. And now we don't have any of those kind of red outlines because we have now defined KD and KP. So KD, that's 0. But just for the sake of, I don't know, feeling better about ourselves, let's disconnect it. Just so it makes more kind of intuitive sense to us that we're only going to tune our proportional controller here. Okay, I'll save this again. All right, and then what we're going to do right now is we're going to run this. So if I run this right now, we also need to change our input rule to 1 degree. See, I forget this stuff. So that's why I have slides here. So the kind of first situation that we have for our closed loop system is setting our input angle to 1 degree. So our step time is 0, initial value is 0, final time is 1. That's going to give us just an input of 1 degree. Okay, no external force, so let's just disconnect that. There we go. So now this disturbance or this bird strike isn't acting on anything. And KP, that's set to 0 right now because that's what we set it as in our script. KP equals 0. Let's actually add in a comment. Proportional controller, and then KD derivative controller. Yeah. See, it's giving us warnings here because some of our blocks here aren't connected. So it's a warning, it's not an error. Okay, so if I run this system, even though it just ran because I ran my script, we can look at the output. Damn it. I didn't want to show this right away. It's obvious though, so if you were going to guess what the output should be, well, it's going to be 0 because we're essentially multiplying our entire system by 0 since KP was set to 0. If I click on the aircraft response, look at that, the output's 0. That's not what we want, so let's start tuning our controller here. And let's see what we get. We want to have a marginally stable system. So let's try KP equals 0.025. So I'm going to go over here. And I'll change it to 0.025. You can imagine we could make some kind of script here to use a for loop or a while loop, kind of depending how you want to go about it, to kind of iterate until we reach some prescribed parameter where our period or our amplitude for our peaks are, within some tolerance. And if they were, then that would say that, okay, now you're at a marginally stable system. Now we're not doing that. We're just doing it kind of like, I don't know, schmucks, where we need to do it manually. All right, so did I set that correctly? Yeah, 0.025. So it's a very small value. It already ran, whatever. But let's check out the aircraft response now. Not great, right? Not great. We're blowing up here at the end. We're kind of going to resonance here, so that's not what we want. Let's actually also go back to our script, and I'm going to add in some code here to make a plot, just kind of like we did above here. So so you see, let's actually, yeah. So our 2 workspace block here, that's looking at our output. And again, this is just called response. So if I go into MATLAB, we see closed underscore loop underscore sim. If I double click on that, then I have a time series that's called response. That contains our time and then our output roll angle. Okay, so let's make a plot. So make a section, closed loop plots. And then we're going to plot, because I have a time series, I only need to specify that variable. So closed underscore loop underscore sim dot, we're using dot notation dot response. And then let's make this red because it's bad. And then line width, comma 2. I can delete these spaces, don't know why I put them. And then let's put in a title. Closed loop response. You know what? Proportional controller response. 4. Put in our $sign. We're writing some LaTeX kind of scripting here. Theta I equals what? Didn't want to do that. What was the angle? 1 degree. For theta I equals 1 degree. No birdie. Make a better name. And then I need to put in interpreter LaTeX. Alright, did I put in? Yeah, okay. Let's run it. There's our plot. So bad news, we're blowing up at the end here. Alright, so we gotta change this, right? So let's try a new value here. Instead of 0.025, we're gonna try 0.0135. I already spoiled the graph again. Yeah. Blame it on being sleep deprived. So you know, I'm just gonna comment this line out just so we kind of know what we first set it as. So in this case, you know, our code doesn't look great. That's why it'd be better to use something like a for loop, but whatever. We're gonna do 0.0135. And now if we run this, we're gonna get our plot that just shows up. It looks kind of cool, to be honest, but it's still bad news. We're not stable. Maybe we're not exactly blowing up, but we're certainly not having a good time here. So we still need to adjust this. So I was going to have you actually work on this on your own, kind of for the lab report. But I'll just spoil it now, just so we can continue to work on our tuning for the closed system. So in the end, if I change this to, I don't have this in the slides because I was going to have you figure it out on your own again. So we're going to finally reach a value of KP. Got to look at my script. KP equals 0.0117. Right now, if I run the script, and there we go. Now we have, this may not be exact. That's okay. You know, for that, you could look at the period for these peaks. For like, you could look at multiple peaks and then take the average, and then you could determine how close you are for kind of, you know, finding that same period. So here it's close enough. Basically, we're going to take this as it is and run with it. So our KP value here is no, I need to comment this out. Okay, KP value is 0.0117. Once we do that, we have this marginally stable system. Okay, so now what we have to do, so we're going to take this right now, and now, because we have this marginally stable system, we're going to call this K star. So I'm going to do K underscore star equals KP. Okay, and we're going to be using this to tune our proportional derivative controller later on. All right, so there we go. Now we're going to do some bookkeeping here. We're going to find T star. So T star is going to be the corresponding period for this setup where we have K star. Okay, so we're going to go back. The toolbox that we downloaded earlier, it might have a function to kind of do this automatically. I can't remember, to be honest. So let's go here. If we look at our aircraft response, there we go. We have our system here, or our response, whatever. And so now what we're going to do, we're going to go to Tools, Measurements, Cursor Measurements, and now we're going to find our period. So we're going to be looking at this value here, delta t. So what we have to do, we're going to drag our first data point. I'm going to go to the first time where we reach our amplitude. So I'm dragging this, and I'm going to look at this row here for 1 for a time. And really, I'm going to look at this column right here, or this value for our value for the first data marker. I'm going to try to increase it for the max value. Okay, there we go. Now I'm going to change our data marker 2. I'm going to go to the next kind of time that we reach our amplitude. And I'm going to try to get to the max value there. Okay, there we go. And so what we have here is 21.669 seconds. You might have something that's different. That's okay. It should be right around 21.7 seconds, 21.8 seconds. It should be something similar to that. There's going to be some variability because MATLAB isn't exact. We're using numeric approximations here, so it very well might be different. Kind of like how it's a little different in my slides. I think I had 21.8 seconds in the slides. And, our resolution here isn't great. Just like you saw the toolbox earlier, that can do it a bit better, where we can actually look at our peaks. So I think we actually can do this. Maybe not here, but maybe the other box, bi-level measurements. Maybe not. There's one of the toolboxes we can actually look at all of our values for our maximum peaks. But this is how I did it for when I was taking the lab, and this is how we typically do it for this lab, where we use our cursor measurements and we kind of find our period manually like this. Again, your period should be around 21.7 seconds or 21.8, somewhere around there. So to kind of just do some bookkeeping, we're going to write that value down in our script so we can reference this value later on. So I'm going to do t_star equals. So I don't think we can write any code to actually just export this from here. Because we found that manually, we actually have to write down that value manually as well. So 21.669, that's going to be t star, and our units for that are seconds. All right, there we go. So cool. Don't know why I ran it. So we have t star now. So we're going to keep that kind of in our back pocket here. Okay, and then all these slides here, they just kind of show you what I just showed you right now. So I guess in my slides, they had a period of 21.45 seconds. But yeah, it should be around 21.8, in this ballpark. Okay, so step 2, if we look at our lab handout. So we just did step 1 in our lab handout here, setting KD equal to 0, our input rule equal to 1. And then we adjusted KP until we were marginally stable. And we put down that value as a 0.0117. All right, so now we're in step 2. We're going to start putting in our, I guess not quite yet. So we're just going to adjust our proportional controller to 0.5 times K star. And we're going to have an input angle this time of 5 degrees. And in your report, you're actually going to kind of do some calculations for what we talked about earlier for the steady state error, the percent overshoot, and the settling and peak times. So basically go over everything that we talked about. I think there was 5 things that we talked about earlier on. Okay, so again, you can either, my stomach is growling, I gotta eat sometime. So you could save this simulation file if you kind of want to save a file for each step. I'm not going to do that. So, at this point, you should save your figure, whether it's now or later on, you should save your figure for this kind of relevant figure for the report where you show our marginally stable system. Okay, so now we're going to change KP to 0.5 times K star. So what I'm going to do here, I'm not even going to comment this line out right here. All I'm going to do is go on a new line here. I'll make a comment. We're going to call this step 2. Adjust KP to K star. So if I do KP equals K star, and this is basically just updating our value for KP. In this case, it's going to be equal to K star. I need to do 0.5 times K star. There we go. So this is essentially just doing 0.5 times 0.0117. And we need to set our roll angle to 5, so don't forget that. We're going to go back into Simulink, change our roll angle to 5, apply, okay, and now we need to save this. Make sure you save it. Because if you don't save it, MATLAB doesn't know what the current value that you have here, so you need to save this file. I think I ran into the issue last night as well. I was kind of going crazy. Okay, now we can run it, and we can look at our response now. So here's our response. We got another pretty cool graph here. We got a damped solution here. But wow, look at that overshoot, right? We had an input angle of 5 degrees, and we overshot that angle up to around 8.5 degrees. And then with time, we get to a steady state response of 5 degrees, so that's good. But it also takes, a really long time. We're at 300 seconds here. So, I mean, what is that? I can't do math in my head. Is that 6 minutes? No one criticize me. That's 5 minutes. Yeah, that makes sense. Okay, so no one wants to be on an airplane where you put in a roll angle of 5 degrees and it takes you 5 minutes to get there. That would suck, and you're oscillating a lot in the beginning. No one's going to be going on that airplane. So we're going to have to do some more adjustments here. All right, so step 3, we're going to change our parameters again. So, you have to save that figure and do some analysis on it, especially for the peak times and whatnot. So now what we're going to do, we're actually going to add in our derivative controller as well to our system. And we're also changing again, or updating again, our value for KP. So I'm going to make a comment. Step 3, adjust KP and add in KD. So KP this time is going to be equal to 0.45 times K star. And so here's K star. K star was equal to KP at this point in time, which was equal to 0.0117 equals. All right, so there we go. That's KP. And then KD has to be equal to 0.125 times KP, which is corresponding to this line here, line 34. So times KP times T star. So that's what we put down from earlier. Here's T star. That's our period. There we go. And we're going to leave our input roll angle at theta equals to 5 degrees. Run it. No function named. Oh, we're still going to have an issue here because I didn't set KD back up in our Simulink model yet. So let me just look at this one more time. K star, that's good. KP, T star. Okay. So we need to go back to Simulink, and we actually have to, connect our stuff here for our derivative controller. And, a good thing in your report would actually be to compare our response for with the derivative controller, so a full PD controller and without. So let's save this, run it. Look at our response here. Okay, so right now this is just with a proportional controller. So we're going up to around, I don't know, 8.2. Make sure it's 5, yeah. All right, let's look up our derivative controller. So we have a proportional derivative controller, run it. Look at the response. Wow, much better. So our overshoot isn't quite as high and we're not oscillating as much in this system. And look at that, our steady state value is reached. Still not great, but it's better. We go to a steady state value. I mean, you would actually have to use your cursor measurement here, but before 100 seconds. So that's still, you know, not great, but that's what we have right now. Okay, and then the next thing that we have, let's actually look at this again. Move this out of the way. So yeah, one of the things we're going to be writing is the how fast it took to get to the peak time. So let's go to signal statistics here. So in this case, it was 17.42 seconds. Yeah, okay. In my head, I was thinking about a different peak time, but that's for what we're about to do. All right, so that took 17 seconds to get to that peak time. Or that peak value, rather. All right, let's close out of this now. All right, so now we're in the last part here. All right, so now we're going to simulate another bird strike. This time it's going to be more violent. So remember, this bird strike is going to be 2 times the force of our first bird strike. So we'll go back into MATLAB here. And what I'm going to do now is specify T2 equals 2 times T underscore 1. Remember, T underscore 1, that was the bird strike at 8 times 10 to the 5th newtons. So we'll make a comment. New bird strike. Okay. Now we need to go back into Simulink though. We need to first connect our bird strike, and we're also going to have to change a value here. We could have also updated T1 to be T1 equals 2 times T1. I guess let's actually do that. So here I'm just going to do T1 equals 2 times T1. And by doing that, I don't have to change anything in here for this step function. I can just leave the final value as T1 for both parts here. And let's see, the roll angle, we have to change that to 0. We could also make a variable for this, so I don't have to actually go into Simulink here. I could just do it from the script. So you could put a variable for like theta I or something like that. So now if we run this, let's first look at our output here. Let's make sure it's correct. Yeah, it's actually not. So it's still doing 8 times 10 to the 5th. So maybe I put this in. Come back. Maybe I put this in at the wrong spot here. We're simulating it right then. I'm sure there's an issue that I'm not seeing this right away. So I'm just going to do T2 equals 2 times T1. Okay, let's go back to Simulink, and now I need to update our parameters here to T2. So yeah, there might be just an issue I'm not seeing right away, but for the sake of time, I'm just going to change these to T2. Oh, maybe it's because I didn't save it. I don't know. Let's run it now. Look at our output here. And now you see, now we're going to 16 times 10 to the 5th instead of 8 times 10 to the 5th. So now that's correct. And if I look at our response here, let's actually look at it inside of MATLAB. Looks a bit better. All right, so if I run our script, let's change our title as well, I guess. So theta I was 0 this time, and we had a birdie. Let me make sure I actually set theta I to 0. double check. Yep. Okay, so now if we run this, then we're going to get our response here. Pretty good. So we had an input roll angle of 0. We had a bird strike at 1 second, and it was a pretty forceful bird strike, pretty violent. And our peak response was 0.5 degrees. So, I guess compared to 0, that's an infinite error there. But we recover, pretty fast here. For considering we had a bird strike. So we peak up, we have this huge overshoot because of the bird strike. And then it goes back down, it kind of overcompensates once again. But because we have our derivative controller as well, it's differentiating that error that we have. And then we can settle down. The settling time might be somewhere around here. And then we reach steady state around this time right here. All right, so there we go. That was the last part right there. So I think I went kind of, a little fast there at the end, but I think, as we started going on with this experiment, hopefully stuff started making more and more sense for what we're doing for this lab. Okay, and then, so for all of the plots that we have where you can measure stuff like, let's go back here. Yeah, the peak response, peak time, overshoot percentage, settling time, and steady state error, you're going to write that in the report. So again, I'm going to make my deliverables document. I'm going to try for today, but today's another pretty busy day, but it'll be up for sure by this weekend. It's going to be up sooner though than by the weekend. So I'm going to do that, but if you want to get started on the report now, you're going to do everything that we just did in this class. Work on your results, your sample calcs, stuff like that. Your sample calcs here, there are going to be stuff like KP, KD, you should specify, of course, for what part in our tuning process this was for, but there's not too many sample calcs here. Also, you have some sample calcs for overshoot percentage and steady state error. And what else? The period. Guess that. I mean, maybe not for the period. But yeah, just think about what we had to do what calculations we did, and you can do that. Work on your results, interpret them, make sure you interpret the results. I don't think there's too much of an issue for this lab, for your first memos. But yeah, just make sure once you have a result that you discuss it below. Make sure it's below the figure. You should present the result first and then discuss the figure. Tell me what's going on. So if we're looking at our graph here, you can't just say, yeah, this is our response for a proportional controller. That should say PD, proportional derivative, because we updated that. So you can't just say, yeah, this is our response for the proportional derivative controller for theta I equals 0 with a bird strike. That's not enough. You need to explain what's going on. So why do I see a sudden increase at some time? Tell me what the time was. Tell me what this value is up here. Tell me why we see that sudden increase. In this case, it's because of our bird strike modeled as a step function. Explain why we're going back down where we kind of had another overshoot here. And explain why we have another overshoot here, and then why we have why we go to steady state, somewhat fast given our impact force. So, you want to discuss some of this stuff here, and then in your discussion, you're going to expand on that. When I say expand on it, now you can draw some conclusions on, maybe you would compare this graph to what a proportional controller would look like given this scenario. Explain why the derivative controller is better in this for this scenario. Let's actually do that really quick here. Let's take out our derivative controller, save it, run it, go back to MATLAB, run it. Look at that. So the first overshoot, it's still not terrible, but because we don't have that derivative controller, it's not differentiating the error, so we can't adjust quite as fast. So I guess I just kind of gave away your explanation for you, but I'm sure you can think that through yourself. And even way out here, we're still oscillating a bit. It's not a lot, but we're still oscillating a bit. So you need to use a cursor measurement, or you could write some code to basically find when we reach a steady state value as well. So I want to see stuff like that, basically, expand on your results in the discussion. Okay, so that's, I guess that's it for today. So it took a while, but I think this is actually a pretty interesting lab, especially if you kind of play around with some of the settings, do some comparisons for the PD controller versus only the proportional controller, kind of mess around with some stuff, and I don't know. So hopefully you enjoyed it at least a bit. And that's all I have for today. So if you don't have any questions, then I'll see you guys next Tuesday. Remember, your Lab 2 memo is due today. And yeah, this will be due in 2 weeks. All right, so that's it. I'll see you guys on Tuesday. Yep. See you, Kyle.
Thanks, Professor.
Yep. See ya.